which was actually asked during the class as well. Which is, why is it in the intrinsic frame, why do we have to have those components equal to 0? I sort of hand-waved it beforehand, saying it was a matter of the Legendre polynomials. Remember, the y plus or minus 1s are basically the Legendre, so 2 plus or minus 1s are basically the Legendre polynomials 2, 1, and then an e to the I plus or minus 1 times phi. So what we're after is this Legendre polynomial of cosine theta. So let's see what those different Legendre polynomials do for us. If we plot the Legendre polynomial P20 as a function of theta, that is this first plot. So we'll see that it adds at theta equals to 0, subtracts at theta equals to pi over 2, and adds again at theta equals minus pi, theta equals pi rather. All right, sorry, theta is coming down like this. So that maintains this, the z-axis as a symmetry axis. All is good, or potentially good. Let's look at Pu21 though. That would be our next plot. If we start with a sphere, we start by adding on 0 at the pole. Then at pi over 4, we add on 0 at the equator. We're subtracting at 3 pi over 4, and by the time we get to pi, we're back to 0. So notice what that's doing. That's trying to give us a shape pointing out this way, which is very much not aligned with the axis we want things to be aligned with. Let us now look at the final one, which is P22. P22 is looking okay. We start by adding 0 at the pole. We add at the equator. And then we get to 0 at the pole again. So let's draw that on both sides. So that looks like it's along the axes. Still, that could be symmetric along the x or y axis. This pen writes in a combination of red and black. That's amazing. Wow. Okay, so that is okay if that happens to be along the correct direction in the equator, the x direction or the y direction. But what if it's going out midway between those two directions? That will all depend on the e to the I plus or minus 2 phi factors. You need the correct linear combination to give you stretching along the x or y axis, not in between. And that's where the condition of reality comes in. For the A2 plus or minus 2 real, we'd have to play with a little bit of trig with those e to the I2 phi's to be sure of that. So I think that's probably a little bit more of an explanation than we had before. All right, so we will now try to cover the rest of physics in 1.5 hours. And the backup on all this is I figured I'd actually write down the bibliographical information for a very meticulous step-by-step, has all the details review of everything here. So if you do need to go back and work on this type of stuff, I very much recommend that as one of the best starting points. So there's some... Yeah. I have had a request for that. I will try to write something up neatly. However, since I can only work at finite speed, it would not be for this afternoon's exercise session. But you actually don't need terribly much of this for the exercise session, I can point out. If there are any...
but this is okay because
yeah.
writing down all these things and understanding as well as difficult for
yeah.
At least me. For
yeah.
If you put that things in the outside, that will be okay because
Okay. 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 So there are some, let's see, so what should we, let's all right, so let's go back to the image we have of what these coordinates mean. we've said that beta and gamma describe a given shape, but there's actually some funny business going on with these coordinates. Different values of beta and gamma, when you plug in what they mean in terms of the spherical harmonics, draw the shape that comes out, will give us the same shape but just pointing in a different direction, which isn't so nice because that's what the Euler angles are supposed to do. The Euler angles are supposed to be what rotate us to a different direction. The reason for this is that we have said, oh, here's this magical approach that aligns our shape along the intrinsic axes, but we never said which should be the long axis, which should be the intermediate length axis, which should be the short axis. There's an ambiguity there. There's actually an ambiguity both in the labeling of our axes and also in which direction they point. There are 48 different transformations you could do on our axes and still have a valid set of intrinsic axes. We have to now, on the other hand, if we're defining a Hamiltonian, there are certain invariance properties we want. When we say that we all know that our Hamiltonian should be rotationally invariant, we're going to be defining a Hamiltonian as a function of this deformation tensor, so basically of the shape of the nucleus. Certainly, the nucleus pointing this way shouldn't have a different energy from the same nucleus pointing this way. So it's natural to say, okay, it should be a rotational scalar. The Hamiltonian should be. But there has to be more than that, because now it turns out we can have, for instance, the exact same Euler angles, but shuffle around beta and shuffle around gamma, and we'll get the same shape, but pointing along a perpendicular axis. So what we need is, moreover, a Hamiltonian that's invariant under any of these switchings. Switching the names of the axes should not affect the energy of your system, is another way of looking at it. I'm realizing now that I should have made some pretty pictures showing different gammas giving the same shape, but pointing different ways. Oh well. So I want to just do this very quickly, so to the point, though, that you get the basic take-home that will come out of it, which is, okay, there's the octahedral group is the symmetry group. You realize it's the same symmetry as an octahedron. There are basically 3 axes for an octahedron. An octahedron is invariant if you flip the direction of either of those axes, or if you rotate one of that set of axes. So permutations and flippings of the 3 coordinate axes are the same as the octahedron, so okay, we have a fancy name for it. The important thing is that you can generate all those transformations from a few basic transformations. Okay, identity transformation, that's trivial. 3 rotations, and then inversion in space. So these are the Euler angles. So like, let's see, this last rotation is the one that permutes the 1, 2, 3 axes into the 2, 3, 1 axes. I can't pretend to quite do it. This is a rotation around the z-axis followed by the y-axis. This is a rotation of pi over 2 around the z-axis. And thing is, these are what those rotations do to the axis labels, but we're interested then in translating that into what those rotations do to the intrinsic coordinates beta and gamma. There's algebra that comes in here, which is not in my lecture notes. It's long algebra. But the point is, this first rotation actually leaves beta and gamma unchanged. The second rotation flips gamma to minus gamma. So our Hamiltonian will have to be symmetric. If we flip gamma to minus gamma, we actually have not changed the shape of the nucleus. Similarly, if we subtract 2 pi over 3 from gamma, we have not changed the shape of the nucleus. So our Hamiltonian should again not change its value. We can sketch what this means in the polar plane. When you have a visual picture of this, it'll be a lot easier. So this means that 2 pi over 3 is a very special angle. So that's 60 degrees in common parlance. So anytime, if you take, say, the potential here, so if we hit, so this is our A0 axis, this is our A2 axis, our deformation coordinates. We're all happy dealing with particles moving in abstract 5-dimensional spaces, right? Natural, every day we do, yeah, okay. So we now, the potential will have to be the same at that point, rotated by 2 pi over 3. It also has to be the same when we go to, so when we take gamma to minus gamma. And again, we can repeat these as many times as we want. So basically, we will have, where's the next axis like this? So again, 2 pi over 3, 2 pi over 3, 2 pi over 3. You've all played Trivial Pursuit at some point? Yeah, so that's the easy way to remember this, these axes. It's the, who has played, who knows Trivial Pursuit? Who does not know Trivial Pursuit? It's okay. You're in fact, you're probably a better person if you don't know Trivial Pursuit. Okay, it's a board game where you have little pie-shaped things with 6 little, and you have to, by answering trivia questions correctly, you basically get different colored wedges that you fill those in with. Okay, so it's just like the Bohr Hamiltonian, it's easy. Okay, so, right, so we have this symmetry. Any set of points like this, Hamiltonian has to have the same values. Okay. So, what does that mean for us? We're talking about Hamiltonians. Let's actually, we've been talking about the potential now. We've figured out the symmetry conditions it has to satisfy, but we're missing a very important ingredient. We still need a kinetic energy operator for our Hamiltonian. Yes?
Can you go over just your thought? So
Yes.
you say your Bohr Hamiltonian should be invariant according to these.
These, exactly,
So
exactly.
it means that we can map all these shapes just going from 0 to 60 degrees.
Exactly.
But what was your step to say that the Bohr Hamiltonian should be invariant against those rotations?
Because if you go beyond, it's a claim basically that these rotations are the ones which just rotate these axes onto themselves with different labelings.
So you can use these D functions
Ye
to do these things? Not
yes,
using- yeah.
that's right. D functions on the spherical harmonics would be one way at least of doing it. It's ultimately coming out of this, I guess, the spherical harmonic properties, and you can rotate, yeah, do a D function to rotate the spherical harmonics, and you would ultimately get this. Gap in logic, I know, yes. Or gap in derivation at least. Okay. So the moral was V of alpha should be a V of beta gamma to be invariant under rotations in general, independent of Euler angles, and then it should be symmetric under these operations, gamma to minus gamma, and gamma to gamma plus 3 pi, 2 pi over, plus whatever, plus, yeah, so ultimately, yeah, to 2 pi over 3. Okay, now for our kinetic energy operator, here's the fun part. We have a very large infinity of possible operators we could choose, right? This is not a real particle moving in Cartesian 3-dimensional space. This is some effective Hamiltonian, which we're hoping somehow comes out of the microscopy for the nucleus. And the question is, does it even have a Schrodinger-like equation governing it? There are derivation modes, there are various approaches that can give you something that looks sort of like a Schrodinger equation with a lot of flexibility in the kinetic energy operator. We will basically only discuss today the leading order term, the simplest one you could imagine, which is say, let's pretend this is what Bohr and Modelson originally did. Suppose this is a Schrodinger equation, and let's look back. We have a set of Cartesian coordinates here, real Cartesian coordinates. We can let our Hamiltonian be the good old Laplacian. Okay, 5-dimensional space, but still the Laplacian. Yes. I mean, let's say a Hamiltonian for these degrees of freedom, which we've decided are the degrees of freedom of our nucleus. So we've two parts of a model. We have a space and the Hamiltonian. Our space here, we've said, let's say that we have these deformation coordinates, and we'll take wave functions on these deformation coordinates. We then need a Hamiltonian for that, and that's where our creativity starts to come in. I mean, historically, this was very much at the level of, okay, in the 1940s and 50s, there was the idea that the nucleus could be treated for certain purposes, like for fission, as a liquid drop. And you could have a classical Hamiltonian for a liquid drop described in terms of these 5 deformation coordinates. And you can follow the quantization procedures for a classical Hamiltonian, and you'll get a quantum Hamiltonian that looks something like a Schrodinger equation Hamiltonian. That is purely at a phenomenological, let's try it and see if it works level. Then there are modern approaches like time-dependent Hartree-Fock, and then quantizing that, and then even, and that's actually, yeah.
So you mean you add some constant to the Hamiltonian?
Right, right.
Like, I mean the formation one? Yes. Like, and in order to get some Gaussian or some constant Hamiltonian, yes? You mean by this effective Hamiltonian, you mean the Hamiltonian with the adding term, like the constant of the formation field?
I'm not 100% sure I understand what you're saying, so let me see if I can say it the way I think, and you'll tell me if it's the same thing. We will be taking some constrained form for the Hamiltonian, like saying, okay, this is the family of potential functions. Well, ideally, we would just take one of these microscopic approaches and get a Hamiltonian handed to us out of that. And there's continuing effort on that. But it's certainly not at the level of being perfect that we can just do that. Whereas today we're viewing this at the level of, okay, let's treat this phenomenologically, but all the machinery we build up is stuff that if someone handed you a Hamiltonian microscopically, you could then use it when we have built up the intuition doing this. I think I got to answering a different question. Okay. Okay. So the idea then was start from the Laplacian in 5 dimensions, but that might not be the form we ultimately write it in. So that's saying Hamiltonian is minus h bar squared over 2b, where b is playing the role of a mass in the Schrodinger equation, but its connection to actual masses is a pretty distant one. Kinetic E beta gamma, and okay, our V of beta gamma. So what is this Laplacian? We're going to fill in a few steps here, and we're going to again have some leaps of derivation. It is immediately intuitive to the most casual observer that this after 12 pages of algebra, that this follows equals minus 2, I guess we're using k for that. K equals minus, no, I don't know what index we're using. Yeah, oh, this was our Cartesian coordinate. So yeah, I equals minus 2 to 2, derivative with respect to xi, second derivative. So this is the Laplacian on R5. Then this could be rewritten in terms of the complex coordinates. So we're going in order basically from least scary to scariest looking. So we've thrown in some complex conjugates. We're getting a little bit scarier. And then it is immediately obvious. Yes, yes, yes. Okay, we have our final form, which is going to, there's not enough room to write it here. So, okay, I'm going to say something in a moment then that will make this look a little bit less crazy. So this is, if we rewrite this in terms of the Bohr values, beta and gamma, we then have plus 1 over beta squared This is on some slide somewhere, so actually maybe we can just go to that. So I'm writing down this thing on the bottom here. Okay, so let's just do this as dot, dot, dot. You have it on the slide here. I've color-coded blue, everything that depends on beta. Red is, can you more or less see that? I'm not sure I really want to get into turning the lights on and off. Red depends on gamma, Green depends on the intrinsic frame angular momentum components. There is one important thing to notice, though. This thing in parentheses, that big, horrible, awful operator, is minus times something we're going to call lambda squared. This is the SO5 angular momentum. It's the 5-dimensional analog of the L squared operator squared. The reason I point this out is we'll have need for it again, but also, yeah, but this should actually look somewhat familiar to you in retrospect. We've done something very similar. Remember, in 3 dimensions, you had the Laplacian, which looked nice and simple, derivative with respect to x squared, y squared, z squared. In Cartesian coordinates, then you did that messy thing, maybe Jackson electrodynamics, of converting it to spherical coordinates, and you got that the Laplacian was equal to 1 over r squared, derivative with respect to r squared d over dr. That's starting to look suspiciously like this. It's just that the power's gone up from 2 to 4. As you might expect, the dimensions go up. Maybe some of your powers will change. Plus 1 over r squared, directly analogous to the 1 over beta squared. I guess there's probably do I have a minus sign missing? I may have a minus sign thrown in for fun. I'm not sure what's going on. Okay, 1 over sine of theta, derivative with respect to theta, sine theta d over d theta, which is very much of the form of gamma here, which is sort of the first angle we've taken out of our set of angles, and then plus 1 over sine squared theta, derivative with respect to phi squared. And in 3 dimensions, this was just the negative of the L squared operator, our squared angular momentum. So that was the SO3 angular momentum. Important to notice, because a lot of that structure will carry, a lot of the things that we did in 3 dimensions, like doing central force problems, where we found that the angular wave function was a spherical harmonic, can be repeated in 5 dimensions. Any questions at this point? Obviously, we have not derived this, but we just claimed it. Yes?
What is at the bottom there?
On the screen?
So the angular momentum term on the right, is it a 2/3 I?
Yes, it is. And you will be getting the slides, definitely. Anything else? All right. So I'm trying to think to prioritize what are the most interesting things to cover. The other thing we stated, so I will abbreviate some things a little. We also said once we have our space and our Hamiltonian, we also need our transition operators. Here again, it's a lot of, you need to know the microscopic underpinning to really know what the correct transition operator is. You can propose something based on what you expect in the leading order, or you can put in some hypotheses, like say, suppose this is a uniformly charged liquid drop, then we can calculate what the electric quadrupole tensor is and write down that operator. In fact, that's the approach that was usually taken. So the idea is, okay, we have to write our operators. The only one that I'm going to write down right now is our electric quadrupole operator. There can be some very general form for it. So Q is the spherical tensor operator of rank 2. It will be, in general, some function of beta and gamma times alpha 2 mu, plus another function of beta and gamma times alpha 2 cross alpha 2 coupled to 2, and so on. But you'll often see the classic form. Basically, if you take a uniformly charged liquid drop, then the quadrupole tensor depends on the number of protons, the size of the nucleus, and then you can look at the surface deformation and see what that gives you for the charge quadrupole moments, and you'll get something that's alpha 2 mu plus some higher order terms. So basically, our coordinate vector also doubles as our quadrupole operator. That's sort of similar to one-dimensional problems where the coordinate x also serves as your dipole operator. Okay. Now, there are a few special cases that we should look at, and then I want to discuss in the time available the general numerical solution. So the basic cases where we can come up with some form of solution without going all the way, actually we're about to answer one of the questions that came up earlier about the coefficients in a rotor, is if you have what would be called an adiabatic rotation. This means a large separation in energy scale between the rotational degrees of freedom, those will be low energy, and then the vibrational degrees of freedom at high energy. Another way of looking at that is that the vibrations are small compared to the deformation. So if you, schematically, if you had a potential, you would expect this type of situation. So here's our V of beta gamma, A0, A2. Generically, so you can have some triaxial shape, and then suppose you had a very deep, very steep potential. I'm trying to draw oscillator. You know, every potential near its minimum looks like a harmonic oscillator. Those contours would close. You could imagine that the nucleus is like a rigid rotor with this particular deformation, but then is able to undergo small oscillations around that shape. This would be a generic case. Now, in fact, the case that you've seen so far is the axial rotor. So I'm actually going to skip the generic case since one never actually encounters that in practice. Here, you would have an equilibrium that's at gamma equals to 0, and then small oscillations around that. Again, what I'm trying to draw here are contours of the potential in the plane. People comfortable picture, you're all comfortable with contour plots, right? Yes. I've seen people get very confused with these. That's why I'm sort of asking and looking quizzically. This isn't meant to mean vibrations. That's meant to represent contours of the potential. Okay. So the basic thing we would do, maybe it is easier to look first at the triax, the generic case. There's something ugly. So if we look at this Hamiltonian, generically, you'd say, okay, well, we can't throw away the derivatives with respect to beta, but if beta is approximately a constant, there will be a domain where this thing basically looks like the second derivative with beta, and then there will be some higher order correction terms. Delta squared, so del squared would basically be second derivative with respect to beta. And then here, this beta could be replaced by beta. Oh, so let's call these coordinates beta naught and gamma naught would be the equilibrium position. So for the gamma degree of freedom, we'd be able to approximate things basically in a leading order. Then there would be some extra terms in the Taylor series by a constant, and we'd just be left with 1 over beta naught squared, second derivative with respect to gamma. And then in the rotational kinetic energy here, we would have notice that these terms on the bottom basically function the 4. So now you can see 4b times sine squared gamma minus whatever is our moment of inertia. So our moment of inertia here, let's write that down, are 4b beta naught sine squared gamma naught minus 2 pi k over 3. Okay, it's an ugly expression, but we have to live with it. But it would be nice if I used the same subscript on both sides, wouldn't it be? Okay, what letter are we using here? We're using kappa. Let's call that k. And then the k there. So we have minus sum k equals 1 to 3 of this now static value 1 over jk L pat prime squared k, where this is now a constant. And this would be nice. This basically, notice what we have here. We have a separable Hamiltonian. And so in the kinetic energy separates into a purely beta part, purely gamma part, and a purely Euler angles part. Life would be great. We'd say, our potential also separates. V of beta gamma is basically a 1/2 c beta beta, I mean the curvature in the beta direction, beta minus beta naught squared. Think of a paraboloid sitting right here. They'll have curvature, different curvatures potentially in the two directions. You could have a cross term, but our symmetries, I think, get rid of that. Plus 1/2 c gamma gamma, gamma minus gamma naught squared. Beautifully separable Hamiltonian. So our Hamiltonian is a rotor plus a Hamiltonian for the beta direction plus a Hamiltonian for the gamma variable. Both of these are just simple harmonic oscillator Hamiltonians with some subtleties, but okay. So the energies would be rotational energies going as L plus 1 plus vibrational energies in the beta direction, which is the n beta that we had a question about earlier, plus in the gamma direction. Where these h bar omegas just come from the mass parameters, where is the mass parameter b, and the curvature. So once we know the curvature, once we know the mass parameter, we could estimate the vibrational energies. Frequency is curvature divided by mass. And then for h bar omega gamma, we have to remember that there's this extra beta naught factor sitting there acting like a mass. So we would have c gamma gamma over beta hag over beta naught squared b. Now there's one fatal flaw in what I've just done. If we go to the axial rotor case, any idea of what goes wrong? Not completely obvious, I guess, until you tried to plug in.
No effective capacity, right?
Yeah, so basically if we plug in 0 here, we'll end up with, for the k equals 0 axis, if we plug in 0 here, we'll get sine squared 0, which is 0 sitting in our denominator, which is not a nice thing when you're doing an expansion. Well, this is actually the intrinsic axis. Yeah, okay, exactly, yeah. So if it's, yes, it's related to the idea, yes, that you could, yeah, yeah. Yeah.
So with your generic V
Yeah.
here, you have the coordinates beta squared, beta cubed, cosine, gamma. So it looks like cosine is going to be decently represented by our harmonic oscillator because you're not going to have a cubic value. But this beta cubed here maybe means less good approximation for in the beta direction. So if you
Well, but we're expanding around a minimum, so it's not, it'll be beta minus beta naught, that's the important one.
Right. Well, I guess my major question is why have these variables been selected out among the...
Oh, over here, you mean?
Yeah.
Oh, yeah, and I'm not actually a fan of writing it that way, so I apologize. Yeah, so these are combinations that, so basically, yeah, so if we look back at what our symmetry constraints were, are Hamiltonians allowed to, maybe a better way of putting this, much better and preferred. This has historical origins in the geometric collective model, basically. The key thing is that we can depend on beta, and we need a function of gamma that has those trivial pursuit symmetry properties, and it's cosine 3 gamma, which has those properties. So it's really, we need a function of beta and cosine 3 gamma. And as we'll see, actually, technically, that's included here because you can take square root of beta squared and then divide it out from beta cubed. The historical reason here was, that will come naturally in a few minutes. I'm just looking at time. Let us come back to what was going on here. So for an axial rotor, we have to fix this up. Yes.
The path line, the Laplacian, you approximate to the equation, the path line.
Oh, yes, yes.
What did you do actually? What is the approximation?
The approximation is basically taking these things, which are variables, and in places where we can, we're expanding them out as beta equals beta naught plus some small difference. Gamma is gamma naught plus some small difference, and then doing a Taylor expansion in that. Yes. So for an axial rotor, J3 is equal, that angular moment of inertia is equal to 0, and as was pointed out, that's because basically we have a shape that's symmetric around the 3-axis, and there cannot be rotations around the 3-axis. Except that the moment of inertia is always defined around intrinsic axes. Yeah. Yeah, it would be clean in some way, but nobody does it because that's the only axis that makes sense to, yeah. Otherwise, you have a generic tensor instead of just 3 moments of inertia. Okay. So gamma naught equals 0. Need a different expansion. And I am seriously tempted, should I actually bother writing it out? Is it worth writing it out? In the interest of time, maybe I'll just skip to the, no, that's silly. No, let's just ... I can write it up. See, that's, once you ask me to put my notes on the web, there's this wonderful excuse for me to skip things and say that I'll put the notes on the web. Okay, so the short version is, except that doesn't make sense. All right, if I skip some stuff later, that's fine. We can skip gamma independent potentials or something like that. They're overrated. Okay. The reason I hesitate is because obviously it's a big mess to actually derive all this. So just take away the general picture here, which is that we get some different operators. We again have a T beta. We now have a T gamma that depends on the angular momentum projection along that axis. So it will depend on K. Our separation of variables will get messier. And then we're again left with something, some difference of angular momentum vectors, components rather, for our rotational kinetic energy. But we will still get a separation of variables. The bottom line is we still get a separation of variables, but where the K quantum number starts coming in. So we still have separation. And our energies will depend on K and L, but also the number of oscillator quanta from the beta part of the Hamiltonian and the gamma part of the Hamiltonian. And those are those numbers that came in the level scheme earlier. So here, before I even write the energies, let's stress N beta, N gamma, K, L, M. I'm using capital N's because there's some ambiguity. Sometimes people, so here's a piece of trivia for you. This oscillator equation is actually the radial equation for a two-dimensional harmonic oscillator. This is a bit bizarre, but the gamma vibrations are actually vibrations in some two-dimensional space. If that means anything to you, then come explain it to me, please. I can't picture it. Okay, L plus 1 minus K squared. So is our rotational energy. So if you ever see mysterious formulas where the rotational energy has a K squared subtracted off, you know that comes from this way of trying to maneuver the separation of variables. N beta plus a half H bar omega beta, that at least is straightforward, plus N gamma plus 1 H bar omega gamma. So that gives you the basic picture. There are some selection rules, though, that the K quantum number can go from 2 times N gamma down in steps of 4. So the way of picturing this is actually what you'd expect if the gamma phonon had plus or minus 2 units of projection along the axis. So imagine how this would work. This is, I believe you had a slide like this from Rick, actually. This becomes much clearer if we have a level scheme drawn. So start off with our ground state, which will generally be K equals to 0. This has, so angular momentum will be 0, 2, 4, and so on. So the point here is that N gamma is equal to 0 and also N beta equals 0. When N gamma is equal to 0, what are the possible K values? They start at 0 and go downward to 0, so it can only have K equals 0. Let's suppose we add in N gamma equals 1, though, still with N beta equals to 0. Our K values will be 2 times 1 is 2, downward in steps of 4, so are there any more K values? Silence either means it's obvious or I've completely dazed you. So we will have K equals 2. So that will have angular momentum 2, 3, and 4, and so on. This energy difference is basically H bar omega gamma with a little subtraction due to this K. Okay. Now if we go to N gamma equals 2, so here's the way of thinking about this. If gamma is the Rick, you don't have an empty coffee cup with you.
No, we're not allowed to have drinks in here.
Oh, okay.
I didn't discover that until after I.
This can only be illustrated with Rick is in the room using an empty coffee cup, by the way. All right.
You want to hold paper? Yeah, Mark, here.
Oh, perfect, perfect, perfect. Just imagine virtual coffee in here. Okay. So with our Legendre polynomial before, if this was our z-axis, we saw that the P2 the gamma degree of freedom would cause bulges around the equator. Now, what was the point of all that? Yeah, okay, so the point is that is also, a superposition of those is this rotational standing wave going around the equator. So you can picture this as actually carrying angular momentum around the equator. If it carries, so that's basically a projection on the equator of some amount of angular momentum, and we actually saw that was an e to the I plus or minus 2 phi, so it would be 2 units of angular momentum around the equator, so that would give us a projection of 2 or minus 2, but we actually saw rotational wave functions are symmetrized in plus or minus k, so it doesn't matter which we use. Now let's say we add another quantum though, n gamma equals 2, then our rule was that k could equal 2 times that, so 4, or go down in steps of 2, that would give us 0, so that again sort of makes sense. If we have plus 2 units from the first, we could then either have plus 2 from the second phonon or minus 2, so that would either get us up to 4 or back down to 0 for the angular momentum of this standing wave around the equatorial axis. In fact, that reminds me, coffee cups aside, there's a beautiful picture of what's going on. So this is like what we were sketching before, where we had our spheres and then added on the Legendre polynomials. Well, what if we start with something that's already elongated along the z-axis and then add on? Remember, our first Legendre polynomial would add more at the poles and subtract in on the sides. So if we have a vibration in the beta degree of freedom, that's adding basically y to 0 on. That will be classically a motion of elongating and contracting along the poles. So picture an extension like this, but with time oscillation, that means that you get a minus sign a little bit later, so it would be subtracting at the ends and adding on the sides, and so on, and then oscillating back and forth with time. For the y to 2, we start with the long shape, so I should do that in black. I know this is off the edge, sorry. That means I have to erase something. Well, you have that version on the board. Maybe this will barely squeeze in on the edge. This will be an experiment to see if this shows up on the video. So then we have a shape that's elongated this way, but we start adding on one side, picture Saturn's ring, but sort of deformed, starting adding on the sides and contracting on the other sides, and then alternate. So I don't know. Yeah, I can't come up with a good analogy there. So that's exactly what we're illustrating here. So that shows oscillations out on the sides or back in. Now, the remaining Legendre polynomial we saw would add lumps at the 45-degree angles. So let's see what happens if you take an elongated shape, start adding nothing at the end, but positive here, negative here, positive here, negative there. What's happened to our shape? It started rotating. So this is actually a spurious mode. At leading order, the shape hasn't changed. It's just the whole thing has started rotating, which is why we actually don't have a vibration corresponding to that. That actually gets lumped into what's going on with our Euler angles and is part of the rotational motion. Thank you.
So with
Yes.
all of these vibrations,
Yeah.
rotations, is the volume always conserved?
There are two answers to that. In the small oscillation approximation, the answer is, so my recollection is that it's only conserved in the limit of small oscillations. If you went to larger oscillations, you would actually include a monopole term correcting. So you'd have to, instead of having a 1, your 1 would have to not be. Your 1 would have to become a 1 plus alpha 0, 0, basically, which would have to change to compensate.
But is this something that the physics requires? Is that the volume is Or should the physics allow this thing to kind of expand?
I don't think we know the physics enough to answer. There's very much the claim that this whole idea of the quadrupole coordinates representing the shape. So, I mean, if we were saying that the shape here is a uniform filled liquid drop, that's not the situation for the nucleus. You can argue that the quadrupole components should be the quadrupole tensor derived microscopically and have nothing to do with the shape even, in which case there's no volume to conserve per se. You can argue that they're a mathematical artifact from a mapping from a bosonic model, for instance, in which case, yeah, there'd be a whole different set of questions. Yeah, so the answer is people have discussed that a bit, and I don't think there's a good answer to that. Or at least not a complete answer. There can be some arguments in terms of breathing modes for what type of elasticity you expect in that direction, but that's, yeah.
Couldn't you
yeah.
argue that two things that experimentally people have studied, the so-called compressibility of
Yeah.
the nucleus, and at some level there is a compressibility, but it takes a lot of energy to compress the nucleus. It's pretty rigid in terms of volume. And these breathing modes that he referred to are up at 20, 30 MeV of excitation energy.
Yeah. But that still depends on the interpretation of the quadrupole things as really being a surface deformation. Yes?
Could you explain how we came to the conclusion that K equals 2n gamma minus 4?
Oh, how many more hours do we have, and what reference materials am I allowed to look at? The basic version is it comes from the spectrum of the harmonic oscillator it comes from this being the polar equation, the radial equation for a two-dimensional harmonic oscillator. So actually, if you look at the spectrum, so this is a two-dim harmonic oscillator, and K is basically the M. A two-dimensional harmonic oscillator is a particle moving in planes. There's one angular momentum, the projection along the z-axis, and basically if you solve that problem, you end up getting this selection rule on what angular momentum can be. That's only half an answer, but that's basically where it comes from.
And
Yeah.
this you can do it with this hidden program, which is available that solves a harmonic oscillator in n dimensions, which
Okay.
I explained just in the beginning.
Oh,
which
okay.
are part of the lecture.
Okay.
Mark?
Yes.
can I make a comment?
Yes.
For the case he has up there with two of these gamma modes, where you get K equals 0 and 4, if you think
Oh, that's right. I should have drawn the level scheme here. Yes,
if you
most
think
important
of-
part.
while he's drawing the level scheme, I'll say this. If you think of K as a projection quantum number, projections add algebraically, not as vectors. And so if you have two K equals 2's, they can either add together to give you 4, or add oppositely to give you 0. That doesn't give you that general formula, but it shows in this case why you get K equals 0 and 4 and not K equals 2. And by the way, one of my slides had this kind of spectrum with double gamma vibration and beta vibration. I didn't spend long on it.
Yes.
Just like
Yeah.
the next question. So if you like to account with this model for some very
Mm.
deformed nuclei, Mitchell,
Mm.
would you go up to K2, K equals 2 band? Because I think this thing would rather work only up to the ground band and maybe gamma and beta band, but otherwise after that it gets a huge mess, so you don't care about these guys.
So yes, there are only a handful of experimental claims for two phonon gamma vibrational bands.
Done by us.
Yes.
I also gave you some reasons why that was in my lecture.
Yeah, but I mean the short answer is things do become a mess rapidly after you get past the pairing gap, and there also are questions of even if you do have an effective semi-class, shape degree of freedom picture, for that to be supported by the microscopy, you can run out of necessary microscopic configurations once you get past a few phonons, and I mean that's all depending on.
Not anymore.
What?
It
harmonic.
Yeah.
In erbium, it's anharmonic. So it's not a factor of 2. It's simplified.
So you get things that look like a collective excitation but don't follow this nice simple pattern but still sort of look sort of like in terms of other observables like a phonon excitation. Let me think what's most important now. I want to introduce the oscillator basis. The rest is less essential because we need the oscillator basis to understand how things are solved in practice. Let me think for a moment. Thinking's dangerous. Let's remind ourselves of the central force problem in 3 dimensions, because we're going to play a very similar game right now in 5 dimensions. So the topic here is SO5 invariant cases, where especially the harmonic oscillator is of interest here. So recall in 3 dimensions, if you have a central force problem, that was one where the potential only depended on the radial coordinate r. And if you solve for the wave function, the first thing you did I brought the energy over to the left-hand side here for some reason. Okay, the first thing you did was you realized that if you try out a solution, r theta phi, being a radial wave function, and it was convenient to get the radial equation to come out nice to divide out a factor of r, that got some terms to go away. You had a radial wave function times an angular wave function. And this angular wave function did not at all depend on your actual radial potential. It was no matter what your radial potential was, your angular equation was the same, and it gave you the spherical harmonics as your solution. So the u function here will depend on the angular momentum quantum numbers, and also will have some sort of radial node counting quantum number. And this solves the radial equation, which I'm going to write out since we'll see that in 5 dimensions we have basically exactly the same radial equation. The only thing that makes it not exactly the same is that it's different. This thing has to equal and then the YLMs came from an angular equation, and the important thing was that they're an SO3 angular momentum eigenstate. That'll be important because we'll see something very analogous when we get to 5 dimensions, and this eigenstate of L squared is what gave us the L plus 1 as our separation constant. Now, okay, that was 3 dimensions. Let's look at 5 dimensions. And my microphone is dangling at my feet. I don't know how long it's been doing that. But if you want to listen to my footsteps again.
Maybe you should reattach it.
Or speak through my feet, one or the other. I'll just talk down to my feet. Can you hear me okay? Okay. So, 5 dimensions. The analogous situation is, well, we're already using Laplacian for our kinetic operator, and now what if we have a potential that's a function of beta only? The harmonic oscillator in 5 dimensions, for instance, will be beta squared potential. It's E and L. Our wave functions are functions of beta, gamma, Euler. We're asking for that to equal 0. We can do a separation of variables the same way. Remember, though, in our kinetic energy operator, we had some different derivative powers of beta floating around from what we had in the 3-dimensional case, powers of r squared. So it turns out that we'll want to divide out a beta squared here from our radial function. So again, we'll have a node quantum number, the n. And then this v here is the SO5. It's often called the seniority quantum number, but it's basically the angular momentum quantum number for rotations in 5 dimensions. Not to be confused with the L quantum number, which is the 3-dimensional rotation quantum number. And then, so our remaining angular wave function, I'm going to call that capital psi, will be a function only of the angular variables, which are gamma and the Euler angles. And just like before, we had L equals 0, 1, 2, and so on. Here, V will equal 0, 1, 2, and so on. This U and V of beta solves a radial equation, which is in fact, in n dimensions, you get basically the same style of radial equation. All that changes, the one little change, is you get an offset. Instead of L plus 1, we'll have V plus 1, V plus 2. Here in 5 dimensions, those constants will keep changing as we go to different numbers of dimensions. Minus E and V, U and V of beta. The angular wave, but this is beautiful because we have the exact same radial equation. Suppose you plugged in L equals 1 in 3 dimensions. That's the same effect as plugging in V equals 0 in 5 dimensions. Exact same radial equation. You can just pick up your solutions from your quantum mechanics class. Every time you see an L, replace it by a V plus or minus 1. Just make sure you get straight which direction to go, which is you have to sit down and think about it for a moment, and you have your radial solutions. Angular solution, this is set equal to 0. Okay, so the angular solution is the SO5 Casimir operator, SO5 angular momentum eigenstate, which basically means, let's refresh our memory what that was. That means those are the eigenstates of this ugly beast in parentheses. The good news is you only have to basically generate them once and you're all set. Just like in practice, spherical harmonics, it doesn't matter how ugly they are because you look them up in a table, right? Same basic idea here. Yes?
So, with this analogy between L and V,
Yeah.
3-dimensional, 5-dimensional,
Yes.
is there an equivalent of like a 5-dimensional angular momentum projection quantum number?
There are 2 ways of looking at that. So, even though SU2 or SO3 is always the wonderful first analogy for understanding higher groups, it's often not quite clear how the things will generalize until you see exactly how they generalize. So in fact, there are, if you look at SO5 by itself, there are 2 so-called weight operators. So it would be like there are 2 different projection operators. the way things are normally treated instead, though, the basic issue is, yeah, in 3 dimensions, an SO3 representation is pretty straightforward. If you have the representation L, you'll have M equals minus L up to plus L, and so you can label all the states just with one projection quantum number. Turns out when you go to SO4, 4 dimensions, you can play the same game, but you will have a grid of states, and you will have 2 projection quantum numbers. Let's call them mx and my, and you can again label all your states with those 2 projection quantum numbers. When you go to SO5, things become a little bit ugly. It turns out you still just have those 2 projection quantum numbers, mx and my, and you start getting multiple states at the same location. So you need some extra missing index or multiplicity index. Okay, so the end is these spherical harmonics. In fact, that's actually a great question, because the other way you can group these states, this would be sort of the direct approach, saying there's SO5 and that's all there is. But we're interested in having good rotational properties, so we actually want to make use of the fact that SO5 has SO3 as a subgroup, and that means that we actually take different linear combinations of states, which don't necessarily have mx and my even as good quantum numbers. And we will label our states by V, alpha, which is this multiplicity index, the L of the state, so the SO3 angular momentum, and the M. And we will get a bunch of states, lots of magic goes on, but you can construct these functions. Again, these are of gamma and the Euler angles.
Can't we just say there should be like an mx and an my?
So that would be the SO5 to SO4 chain of labeling. We actually will take linear combinations of these that have an L that are so you can think of it as alpha and L, taking alpha, L, and M taking the place of mx, my, and whatever extra label we need. Yeah.
Can I add a remark?
Yeah.
To that? For instance, if you have O5 and you have V equal 2, then it has L equal 2 and L equal 4. And then it has, of course, for L equal 2, 5 projections, and for 4, it has 9 projections. So you can classify them in M, but you will have then 5 times from plus 2 to minus 2 twice, and then from plus 4 to plus 3 and then once.
In fact, this we can jump ahead showing for each V, what are the L values you get. So it turns out for L equal, so V equals 0, you only get an L equals 0 state. This is sort of, you can think that's sort of like for the spherical harmonics, Y0 only has the M equals 0 substate. That's a really bad analogy, sorry. For V equals 1, you have only an angular momentum 2 state. Then for V equals 3, you have an angular momentum 2 and angular momentum 4. Then for V equals 3, of course, what we would guess, we have a 0, 3, 4, and 6. I mean, there are patterns to this. You can come up with rules for it. But at some level, it's also, it's the type of thing which you write a computer code for and then use that computer code from then on. Rather, it's not something you want to rederive by hand every time. Now, as Pete was talking about before, this harmonic oscillator in 3 dimensions, remember, it had further degeneracies than the degeneracies provided by angular momentum itself. Similar thing will happen here in 5 dimensions. In addition to these degeneracies provided by the different L's within a given seniority, we also will have additional degeneracies. So let's go ahead and just state what the angular momentum, the harmonic oscillator solutions are before I get too abstract about this. So let's go back actually and look. We've said we can port over our solutions from 3 dimensions directly to, yes?
How do we get that L value if we have some V is equal to 0 or V is equal to 2 and like that?
Oh, with several years worth of work. No, seriously, it's the branching rule. So that's actually a very general problem. If you have, and it's actually exactly the same as you'll have in the interacting boson model. We are asking basically for if you take a representation of the group representation of the group SO5 and you try to break it up into subspaces that are representations of the group SO3, the answer is rarely simple to a question like that. I could actually give a mini lecture on it. I actually have slides for a mini lecture on it, but I don't think I should use our last 20 minutes for that. The basic argument, no, I will not try to answer it. Okay. But basically, don't worry that's not obvious to you, since it should not. If it looked obvious to you, that would mean you're misunderstanding something. Okay. So let's look back at the three-dimensional harmonic oscillator. We get our radial equation with some L plus 1 sitting up there. That L is what sits down here in our oscillator functions, which involve a Laguerre polynomial, where that L shows up in the order of the Laguerre polynomial. We have some Gaussian, we have some extra factor of R sitting out front here. That means that the five-dimensional harmonic oscillator will have basically the same solutions. So here, the harmonic oscillator in 3 dimensions was V of R equals R squared. In 5 dimensions, it's V of beta equals beta squared. So our radial equation is minus h bar squared over 2b d squared over d beta squared, minus the only difference being we have this v plus 1, v plus 2 here, over beta squared, plus c over 2 beta squared minus e n v. U n v of beta equals 0. So when we do the transformation of L goes to v plus 1 in our 3D solution, we'll end up with u n v of beta will be basically proportional to, okay, the factors out front may depend on normalization, so take this with a grain of salt. R over b, v plus 2. So this is an important point. When you talk about the harmonic oscillator basis, remember that that depends on how wide or deep, what your coefficient of your harmonic oscillator potential is, which shows up in your functions as a oscillator length parameter b. This is important in the shell model. It will be important here in the geometric model as well, because it means that for any oscillator basis, there's the choice of an overall length scale for that basis. But let me finish writing this down. R over b squared. I think you get the basic idea, though. 1/2 R over b squared. Let us skip Davidson models, Willits-John model. Let's get up to the punchline here, which is suppose, so you could imagine other, okay, I promised in the syllabus we'd cover it, so okay, there, we've covered Davidson models. So seriously, there are, just like in 3 dimensions, there are a handful of cases that you can solve analytically for radial potentials. Those, of course, immediately carry over to 5 dimensions. So one thing is, we know that we can solve a potential that goes as r squared or beta squared. Well, what if you add, so here's the very brief version. What if you add 1 over beta squared plus beta squared as your potential? Or in fact, let's write this more neatly as, let's write that as beta naught over beta minus beta over beta naught squared. Isn't that cute? Beta naught then basically that parameter determines where we've placed our minimum. square this out, you'll get a beta squared term and a 1 over beta squared term. Why do we immediately know that this potential has to be solvable? If you look back at the Schrodinger equation. We can combine it into the beta squared there. So if we took this as, if we have a 1 over beta squared, let's say a beta naught squared over beta squared here, plus a beta squared over beta naught squared, this was just our good old harmonic oscillator potential, and this can be absorbed in. It just, again, shifts. It's like effectively changing our it's adding to the centrifugal term. So it's sort of like shifting your angular momentum, maybe by a non-integer amount, but the differential equations don't actually care about that. So this is also a solvable case. You can imagine a very stiff case. So what do these potentials all look like in the beta gamma plane? That's actually worth mentioning. Sorry. Let us, where do I erase? Over here. It's actually often, I think, one of the hardest things is remembering to transform these back into the plane and see what they look like as potentials, as contour plots. So we have our harmonic oscillator, which is V of beta equals beta squared. You can also look at those Davidson potentials, which would be having a minimum at some point here, beta naught, and then climbing up from there. And then we have the Willits-John limit, which is very stiff about beta naught. So actually, Davidson potential, when beta naught goes to 0, becomes a harmonic oscillator. When beta naught goes to infinity, basically, it's not quite obvious maybe, but becomes basically the situation where you're confined to a rigid beta value. And that case, that's sort of like the axial, it's like the rigid rotor. You get a very well-defined spectrum, and that was the spectrum that was shown somewhere, shown here. Energies go as seniority, some constant times the seniority plus 3, as it turns out, all from these rotations in gamma in the Euler angles. So these, the reason I'm pointing it out is keep that in mind. You'll be hearing more probably from Jan about the O6 symmetry of the IBM, and this is basically the analog of the O6 symmetry. So a geometric picture you can keep in mind. All right, in the remaining 10 minutes, we're going to do the next 30 years. Yes?
And gamma, in this case,
Yeah.
what is the potential?
So the point...
We put some delta so we can fix gamma? Or?
No, so the whole point here is independent of gamma. That's the central... completely flat. It's very much like for a central force problem in 3 dimensions, it's completely flat in theta and phi, the angular variables. Yeah, the moment you throw in a gamma potential, we lose this separation of variables. Oh, yeah.
How do you, I mean, it's gamma unstable and gamma take the whole degrees from 0 to 60. How do you picture this geometric
Floppy shape.
floppy shape?
Floppy shape. It is arguably much more for the mathematical convenience than for, there are some physical cases you will hear about that look like they're, well, it's natural in the case of the harmonic oscillator, because small oscillation, if you have a spherical shape, it doesn't really matter whether you're going to prolate or oblate, it's just different parts bulging out. It's when you're starting from a well-deformed shape, having that floppiness is a little bit harder to do, understand. Yes?
I think that the physical meaning of the Davidson model and this following one, like why do you put like 1 over b squared, beta squared, what is the meaning of this potential? And
So yeah, so
you said something in order to get this parabola, you put this 1 over beta squared?
so let's step back maybe and think what we're after. There's the idea that any oscillation, if you have a minimum that, so if we're willing to take for a moment that we're interested in gamma soft potentials, so without trying to explain, we've already said that we can't explain that. Taking that as a starting point, we can ask, well, what would we be interested in for beta? And one thing would be oscillations around some equilibrium. Now, as we all learned in mechanics, at some point around every equilibrium, no matter what potential you take, it will look more or less like a oscillator around that equilibrium. So you can view the Davidson potential as a nice way of mocking up a soft oscillator around some minimum. You could choose any potential there in principle, but if you chose any potential there, you wouldn't be able to solve the problem. So we're basically working backwards and saying there is one potential which, because of mathematical quirkiness, we're getting one of the two terms in the potential looks just like the centrifugal term. We can play some mathematical games and absorb it into the centrifugal term. We can then actually solve it analytically. That's why it became popular in chemistry, and that's why we are using it. In fact, right, so there's no deep physical reason to use the Davidson potential versus some other potential with a minimum there. It's purely mathematical convenience, I would say.
So you mean we invent the potential?
If you are looking for the solvable cases. Now that brings us very much to the next point, which is at some point you have to roll up your sleeves and actually solve a general Hamiltonian. So, in the remaining 6 minutes, let's do that. Okay, no, but there is actually a point. If you are solving a general Hamiltonian, you need a way of solving it. One dimension, you'd say differential equation, just set up a grid of points and do some piecewise, pointwise solution. We, though, want solutions in 5 dimensions with definite angular momentum. You can do that type of thing on a 5-dimensional solution mesh, and it still is probably nothing compared with the people who are trying to model the weather over 1-week periods and something like that. But it still is not necessarily the most convenient way of going about the problem. There's another way of going about such problems, which is, I won't say the only way that's used in nuclear physics, but a common way, and the way you will be using in the exercises this afternoon, which is rewriting a differential equation in terms of a basis, so a problem in terms of a basis, and therefore turning a differential equation problem into a matrix problem. How many of you have actually done this in some form or another in exercise at some point? Yeah, surprising numerical, so a few people, okay, you have, should be in quantum mechanics courses. The formalism of it, that you can write any linear operator as a matrix, usually is included. Hands-on calculations aren't necessarily included. So suppose we had the solution of the Schrodinger equation in 1 dimension that we were after. Let's have a differential operator here for a Hamiltonian. We have a Schrodinger equation as a differential operator eigenproblem. We're looking for a wave function and its eigenvalue. But we can turn that wave function into a bunch of coefficients, a, k, by expanding that wave function in terms of a basis, these functions phi sub k. What would you probably choose if you were looking for a basis in 1 dimension? You'd say, hey, there's one problem we've ever solved. That's the harmonic oscillator problem. So you would use the harmonic oscillator functions. We know them in terms of Hermite polynomials. We have games we can play with creation operators and so on and so forth. We would use that as our basis. So suppose the red function here was the function we were actually after. Well, we'd expand it. Sorry, I don't know what I'm doing. Okay. Suppose the idea here is if the black function were the function we're actually after, we would get it by expanding it in terms of these red functions. The basis functions, here's our first one, here's our second, third, fourth, and then there we get our final result. The way we do that is by rewriting our differential operator as a matrix operator, and the entries of that matrix are, amazingly enough, called the matrix elements, by which, though, we have the added meaning here of sandwiching the operator between the bra and the cat. And voila, we have a matrix to diagonalize. So we're working now in 5 dimensions. We need some well-behaved functions that we can easily calculate the matrix elements of things like the kinetic energy operator in. And so the basic approaches are the geometric collective model used in oscillator basis. And so to give a very brief idea, so there's a lot of terminology floating around. involving very vague and fuzzy distinctions. So if you're looking for absolute definitions, they probably won't be there. It was basically the Frankfurt School, starting with Gnois and Greiner, used the approach which has given its name as the title of this lecture, in fact. GCM, also called Generalized Collective Model, but not to be confused at all with the Generator Coordinate Method, which also has the same acronym, which uses five-dimensional harmonic oscillator basis. And the merit there is it's easy to calculate matrix elements of polynomials in alpha 2 and pi 2. The reason for that, you can imagine, is harmonic oscillator creation and annihilation operators are written in terms of alpha and pi. So anything that's a polynomial in those is basically a polynomial in creation. Annihilation operators work wonderfully with the oscillator functions. So the basic approach was you'd have a kinetic energy, which might be pi cross pi coupled to 0. So this is basically the Bohr kinetic energy. But you could also build higher order polynomials. You generally want the kinetic energy to be quadratic in momenta, but you could say stick in a factor of alpha in between and couple those up to 0. And you could go further if you wanted. And then for the potential, now we have this double constraint. We want the good symmetry properties, but we also, those octahedral symmetry properties, but we also need polynomials in alpha and pi, and that answers the question that came earlier of why do we have, why did we write our potential in terms of beta squared? Well, that's basically this guy, and beta cubed cosine 3 gamma. Yes, that seemed like a funny bunch of variables to use, but it came out of this picture where we're sort of constrained to polynomials in the coordinate. In the remaining 20 seconds of the lecture, we have only about 20 slides to go through. So, so the algebraic collective model approach separates out radial functions. So it uses Davidson radial functions with these psi SO5 harmonics, spherical harmonics, and it actually allows us a bit more flexibility in the operators we can deal with, since there's an SU11 algebra for the radial functions. So without going into great detail, that allows us basically to take any powers of beta and cosine 3 gamma. So a bit more flexibility. There's some cases in which it converges more rapidly, but it's basically just a bit easier to program. And hey, I did it, so that's what you get. I mean, it was David Rowe who originated it. I have a wonderful Mathematica notebook that you'll be playing with to do calculations with it this afternoon. When I say things like wonderful, it's tongue-in-cheek, of course, but oh yeah, it is wonderful. Okay, so let us, right, so that's the idea. So here's the issue. We now have, what you're going to do, this is so, as you know, I've gotten into ab initio things much more recently. This was so funny coming back. This basically, I was dusting off my thesis for a lot of the material here. Right, your thesis is when you actually have to understand things and write them down carefully, and that may be the last time you ever do that in your life. So, theses are very useful things. Dump everything in your head in your thesis, because at least that's a nice checkpoint that you can always go back to. So, an example. You will reproduce this example, so I just want you to see where it is. 102 palladium looks sort of like a harmonic oscillator. Except notice the second 2 plus is raised a bit. Oh yeah, we never drew the harmonic oscillator spectrum, did we? You saw it on Rick's slides, so you have it all memorized, right? Okay. No, so the idea with the harmonic oscillator is that you have a 0, you have a 2, you have a 4 and a 2. This is to be expected because you have a gamma soft problem. and these are what you would get as you would expect in a v equals 0, v equals 2, v equals 4 multiplets. But then you actually have another degenerate 0 here, which is a v equals 0 state again, and with a different radial wave function. So these are the n equals 0 radial excitation functions. This is our n equals 1 radial excitation, and so on. So you expect a 4, 2, 0 degenerate multiplet. But as you move away from the harmonic oscillator limit, this state moves up. So we're seeing a bit of that there. But we also see the 2 plus raised a little bit. So it looks like it's starting to turn into a gamma band. Gamma vibrational band would be one interpretation. So it's not so surprising then that we have something that looks sort of like an oscillator, but not quite. It's a little bit more deformed. So there's a minimum out here at non-zero beta. So it looks a little bit like a sombrero or a wine glass or whatever you call it, a wine bottle potential. And then also it's made a little bit deeper here at gamma equals 0 to raise the 2 plus up a bit, and voila, you have a fit of sorts to 102 palladium. Is this the best fit you can get? Well, so the question is, how many terms are you willing to include in your Hamiltonian? We basically truncated this at beta q, the first 3 terms, the conventional, the leading term of the kinetic energy, plus a beta squared, beta cubed cosine 3 gamma, and beta to the 4th potential. This gives you, in general, for a while I used this slide in every, I think I used this slide in every single talk in some variety or another for about 5 or 6 years of my life, so I'm so glad to get to use it again. These are the, you have the idea, with that type of potential you can get everything from the harmonic oscillator to a gamma soft deformed potential to an axially stabilized rotor potential with a minimum at gamma equal to 0. So what do I want to say at this point? Yes? This is very much for the low-lying levels. At the time I did it, although we actually dusted off this fit and we're looking at the high-lying levels for Daniel's thesis experiment. Is that what your question was getting? Yeah. Yeah. A lot of this was mostly applied at low spin. Things happen at high spin that can completely mess this up. Pairs of particles start recoupling and ugly things happen. Although, yeah, you can try to push this further into high spin, actually. So I am going to point out just one final thing. So how do you do a fit? With difficulty, you can either do automated fitting, or you can get a much better feeling by making contour plots of your parameter space. You've probably seen high energy talks where they're trying to figure out the neutrino mixing angles, and they have these various different constraints, and they look for the point where these different constraint regions overlap. How many people have seen talks like that? Okay, so at least some people have seen high energy talks going on. All right. So you can also imagine doing the same type of thing here. There's something worth keeping in mind. I think I had better close up, though, and ask if there are any questions. And again, we went quickly through this last part, but you'll get to play with a bit in the exercise, so you'll have this the slide to refer back to.